The time, t in minutes, that a particular flight arrives later than its scheduled time is uniformly distributed with t between -30 and 60. The population mean is 15 and the population variance is 675. So let's just do the square root of that to get the standard deviation. Square root of 675 is 25.98 and so on. So sigma is 25.98. A sample of 30 arrival times is taken and the sample mean is calculated. So note this key number 30. So what we can say is that we expect T bar to be normally distributed with a mean of 15 and a variance of 675 over 30. So what we're looking for here, probability that T bar is between 10 and 20, we can just use our calculator. So we're going to use a normal CDF with the lower of 10 and an upper of 20, and our sigma would be the square root of 675 divided by 30. Oh, square root of 30. And our mean is 15. And we'll just calculate 0.7082. If a large number of samples, each with 30 arrival times, is taken, sketch the likely distribution of the sample mean T bar below. This is really difficult to do with any sort of accuracy. We know the mean is going to be at 15, so we need to make the peak there. So standard deviation, remember 68% within one standard deviation either side. This is almost that. So what we've got to do is not take that down to 0 too quickly here. So just try and get our bell shape in, and oh, that's terrible. So we need it to do this and get down so it can hardly be seen. But I mean, this is not a great drawing. But what I would indicate here is that's 0.7082 in there, perhaps one standard deviation either side. I've actually missed the 20 there. You get the idea. It's really difficult to get all three of those marks, I think.